Welcome to nLIGHT's presentation of Corona, a breakthrough in metal processing enabled by programmable fiber lasers. Presented by Dahv Kliner, Vice President of Fiber Laser Technology.
I'll start with just one slide introduction to nLIGHT for those of you who don't know us. nLIGHT is a manufacturer of high-power semiconductor and fiber lasers. We were founded in 2000 with the semiconductor lasers. We're headquartered in Vancouver, Washington in the US near Portland, Oregon, but we have a global footprint in terms of manufacturing, sales, service, and applications. We were 191 million last year. As I said, we started with diode lasers. We introduced an industrial fiber laser product line about 5 years ago, and we've been experiencing about 30% growth in those 5 years. Today's presentation will really focus on industrial applications, but we also have products serving microfabrication, aerospace, and defense applications as well. As I said, we entered the industrial fiber laser market about 5 years ago, and this slide explains why we did that, what we were trying to accomplish. As I think most people here know, fiber lasers have really been revolutionizing industrial materials processing because they improve both cost and productivity. And this has enabled fiber lasers to displace legacy lasers as well as non-laser technologies in existing applications, and very excitingly, enabling some new applications that could not be accomplished with previous technology. As a result, fiber lasers have been the highest growth part of the laser market for at least the last decade. But despite this tremendous success, users have identified a number of shortcomings of existing fiber laser sources. In particular, they have a high back reflection sensitivity, which can result in process interruptions, materials limitations, and ultimately even laser instability and damage. Also, they have limited serviceability. Fiber lasers are generally quite reliable, but of course they do sometimes need service, and the legacy fiber lasers result in excessive downtime because you basically have the fiber laser manufacturer in between the tool integrator and the end user. And so this has really prevented tool integrators from providing world-class customer service to their customers, the end users. And finally, there have remained some very important applications where fiber lasers still perform worse than previous lasers, particularly CO2 lasers, and the very important application of oxygen cutting of thick steel. The edge quality is still better with CO2 lasers, forcing tool integrators and end users to decide between the technologies. In addition, there are a number of emerging applications that would be enabled by more advanced performance, things like faster modulation rates, power tunability and stability, and tunable beam quality. So our goal in introducing industrial fiber lasers was to solve all of these problems while of course not sacrificing all of the benefits that made fiber lasers so successful to date. Our first series of fiber lasers that came out starting 5 years ago really addressed the back reflection sensitivity, the serviceability, the modulation rate, and the power tunability. And I'd like to just briefly touch on those before getting into the newest development to address the other needs. With respect to back reflection, all nLIGHT lasers incorporate hardware-based technologies to suppress back reflections that basically make these lasers impervious to back reflections under all real-world conditions. Now, this is, as I said, hardware isolation. Many lasers refer to having protection against back reflections as software, meaning they attempt to detect a back reflection and shut the laser off before it's damaged. Even if this approach is sort of nominally successful and protects the laser, it's a failure from the standpoint of the end user because their process stopped, their productivity went to zero. In contrast, because we have hardware protection, we do not shut off the laser, it simply absorbs the back reflection and keeps processing. And we also have no requirement to modify the recipes or the tool configuration. You simply use the laser in whatever process you want and it will be fine. As a result, we're the only laser manufacturer who can offer uninterrupted processing of highly reflective materials without any material restrictions. It's also important to point out that this protects not just for normal processing, but against various process excursions, things like out of focus or loss of cut situations. And as a result, we have customers who are cutting and welding and doing additive manufacturing, not just of copper and aluminum, but even things like gold and silver. This is an example of an additive manufacture part of pure copper, where the institute that did that said they couldn't write a single line of copper with a legacy fiber laser because the laser would just shut off. Yet here they were able to build the entire part. Second, serviceability. There are several aspects of the laser that are designed to maximize uptime. First of all, we use high reliability field-proven components. As I mentioned, we started with diodes 20 years ago, and of course our diodes as well as our fiber are in our lasers. In addition, the laser is outfitted with a number of sensors to allow rapid remote diagnosis of any problems so that the repair can be done quickly and efficiently. We have various design features that make the laser fully serviceable in the field. It doesn't have to be taken away from the tool or to a clean room or a depot. It can be serviced right there in a dirty factory environment at the tool. And finally, maybe most importantly, we actually have a training program to enable tool integrators to perform all the key service functions themselves. So the tool integrator can now take ownership of the end user experience without having the laser manufacturer in the middle. We're of course there to support and provide whatever is needed, but we empower our customers to take over the service function. So that's all I want to say about these initial offerings. Now let's get to the new material, which is a laser with tunable beam quality, and then we'll see how that impacts this, this benefit of CO2 lasers, the good edge quality, as well as some other applications. So it's been known even since the CO2 days that the metal processing performance depends on the beam characteristics. Things like beam size, beam shape, beam divergence. This is actually a trade journal article from 2007 from Rofin looking at the effective processing with a Gaussian versus a donut, a CO2 laser beam. So the importance of the beam shape has been known for a long time. In the most important market of cutting, it's known that if you want to cut thin metal, you use a small beam to cut as fast as possible. This is sort of a notional graph of cutting speed versus thickness, but the numbers are reasonable. And so if you want to go fast with thin material, use a small beam. The problem is you can't cut thick in that way because the kerf is too narrow, so the melt won't get out, but basically re-solidify and weld the part back into the skeleton. So if you want to cut a thick material, you go to a large beam, but then you have a substantial speed penalty with thin material. The idea is that if you had a laser in which you could tune the beam quality, beam size, you could maintain the maximum speed over this full range and have a much more versatile or universal tool. In welding, it's known that a small beam gives you a deep weld, often known as a keyhole weld, whereas a big beam will give you a more shallow conduction weld, which can be beneficial for weld quality and also aesthetic reasons. And finally, in an additive manufacturing or 3D printing, a given part will have many different feature sizes, and the optimum beam size will depend not just on the feature size, but on the material itself, its thermal conductivity, the height. And it's very important to maximize the build rate. And so to maximize the build rate, you want to really be using, the right beam for each step of the process. Unfortunately, most lasers actually have fixed beam characteristics. You can't actually vary their beam. And so many approaches have been attempted to give you some amount of beam variability. The most simple involve manually changeable free space optics, things like changing the focusing lens and the cutting head. This, of course, is not a high productivity solution. It's not automated, and you also risk contaminating the lens or the head. More automated solutions include things like motorized free space optics and things like zoom process heads or motorized fiber-to-fiber couplers or switches. And these free space optical approaches also give you some amount of tunability, but at the cost of adding a bunch of free space optics, which adds size, weight, cost, and also new failure modes. Finally, More recently, there have been a family of solutions, sort of beam combination solutions, shown schematically here. The idea is your feeding fiber, the delivery fiber from the laser, might have, say, two zones, a central core and a donut, and then you have a combiner that launches different laser sources into these zones. And so, at the time the laser is manufactured, you choose how you want to partition your various lasers among these zones, and then you can get effectively different beam shapes by turning off some of the lasers and only turning on the lasers in the zone you care about. What these methods have in common is they've all shown the usefulness of being able to vary the beam, but they all increase the complexity and cost of the tool and or degrade the performance and reliability. And as a result, despite all of this work, most tools actually still just deploy a fixed laser beam. And they suffer a non-optimum performance, a lack of process versatility. A given tool often has to limit its job mix, and a job shop might have to buy multiple tools, for instance, a thin tool and a thick tool, or fiber laser and CO2. So we took a fresh look at this problem and said, okay, well, to address this clearly long-standing, widely felt need, what are the characteristics we want in the laser source to solve this problem? And we came up with this list. We'd like it to be all fiber, no free space optics because of the performance degradation, the cost, thermal lensing, things like that. We want to be able to use a standard fixed optics process head, just a normal cutting head, welding head. Of course, one could use a zoom lens, but we don't want to require it. We want the beam tunability to be integrated into the laser, not to require a separate process fiber, which again drives cost and new failure modes. We want the full power to be available in all the beam shapes. We want the end user to be able to use 100% of the laser power they purchased in 100% of the jobs. We need quite a bit of versatility, as I'll show you, in the power distributions. We don't just say we want a top hat beam and a donut beam. We want to be able to do different size top hats, different donuts, different thickness donuts to optimize for all the different materials and processes. And last, we want to be able to do fast switching on the fly, to be able to basically vary the beam shape, just like nowadays you'd vary the laser power, the modulation, to have a real-time switching so you can optimize not just different materials or different thicknesses, but even different steps, cutting versus piercing, straight versus cornering. So we actually came up with a product that does that. It's known as Corona. It's a fiber laser that uses an all-fiber technology to enable continuous tuning of the beam size, shape, the corresponding BPP, etc. Of course, what you just saw was just a cartoon of the laser, but this is not a cartoon. These are actual beam images, in this case recorded at 4 kilowatts. The color jumping is just the camera adjusting its exposure time to stay on scale. The full 4 kilowatts is available in all of these shapes. And so you can see it switching between the various shapes. You can actually see what's going on here. Basically, the feeding fiber is divided into zones. In this case, a 100 micron core, a 200 micron donut, and a 300 micron donut. And we're varying the partitioning of the laser beam among these zones to get these different beam sizes and shapes. Again, this is one laser being partitioned among the zones. It's not multiple lasers. This change is happening directly from the fiber laser with no loss of all of power, stability, reliability, all the characteristics we like about fiber lasers. Being all fiber, the technology is highly reliable. We did an accelerated life test in which we cycled the beam through these settings more than 13 million times with no measurable change in the beam characteristics. So very stable, as you would expect out of a fiber. It's also important to point out this isn't a single product. This is a very versatile platform, and if you come to our booth, you'll see several variants of this product now. We can get a number of different specs, different beam sizes and shapes, different power levels, simply with different fiber designs. The beam is actually continuously tunable, but we found it's actually better to offer a fixed number of beam shapes. And the reason is these lasers tend to go in very electrically noisy environments. So if you had an analog control signal, it could be unstable over various time scales, seconds, minutes, days, years. and then the beam would change over those same time scales. Because we want the beam to be very stable, as I showed in the accelerated life test over millions of changes, we instead give basically a digital selection where we fix the beam shapes and they're digitally selected and then they're stable over seconds, minutes, days, years. This also facilitates process optimization. So in the first product, the beam size went between about 100 and 350 microns. It starts with a small flat top, 100 micron flat top. This is a 200 micron flat top, 200 micron donut, a 300 micron fat donut, and a 300 micron thin donut. The corresponding BPP values vary over this range. Now, in the case of welding, we found that one wants to have much finer control of the division of the beam among the zones, and so we offer significantly more settings where we put, say, 10%, 20, 30, 40, 50% into the first ring, etc. So a much finer control of the beam. What you immediately see is that this technology gives you a very versatile beam sizes and shapes. I mean, I've shown you different flat tops, donuts, flat tops with shoulders. Currently, it's available over a power range of 3 to 12 kilowatts. In fact, it's limited only by the power handling of silica fiber, exactly the same as a fiber laser, because it's silica fiber, just like a fiber laser. So it's basically anywhere you can use a fiber laser, you can use this technology. And as I mentioned, 100% of the power is available in all of these different settings. In terms of switching, here's some camera measurements, a fast CMOS camera showing switching from the smallest flat top to the biggest donut. So we're recording with 5 millisecond time resolution over this range. So you can see after 10 milliseconds, the power is moved out of the center to the rings. After 31 milliseconds, it's moved to the outer ring, and then it basically just stays there. So if you plot this as a diameter as a function of time, what you see is that the switching is finished in less than 30 milliseconds. In fact, with a faster camera, we've shown it's about 20 milliseconds. And in addition, the beam is very stable after it's switched. You see the diameter is staying stable to better than a micron. And as I said, we've actually measured this over millions of cycles, and it remains very stable. It's important to note that this switching is happening while the laser is operating at full power. There's no need to blank the laser. These adjustments can be made on the fly, just like you could vary the power on the fly. And what this allows you to do is optimize these different process steps, and I'll show you an example of that. So that's enough about technology. Let's now get into the applications and see how this has been put to use. And this is expanding sort of every day, so I'll show you some very up-to-date stuff. Let's start with this long-standing need I told you about, auction cutting of mild steel plate. And this is where CO2 lasers until now still did better than fiber lasers. So this is a 25 millimeter mild steel cut with a standard fiber laser with a 100 micron core. And here it is with Corona with this donut beam. And you can just see visually how much better the edge quality is, better roughness, edge straightness, perpendicularity. In fact, it measures out to be a factor of 3 less rough. With this standard fiber laser, in fact, we wouldn't even consider this a successful cut. Do you see all this slag at the bottom? This is this resolidification I mentioned, where the part got welded back into the skeleton and would have to be sort of hammered out sometimes. So that's really not amenable to sort of 24/7 lights out automated operation. Whereas with Corona, because of this excellent edge quality, you have very reliable part drop. Here's some results actually from HK. They're the largest tool integrator in Korea and one of our first Corona customers. They introduced a series of cutting tools based on Corona, and they also make CO2 tools. So they wanted to compare Corona to CO2. And so this is 20 millimeter mild steel. One of these is with Corona and one is with a CO2 laser. You can try to guess which one. They don't just look similar. In fact, all the measurements they do of speed, roughness, perpendicularity, the parts are indistinguishable. It turns out the top one is Corona, the bottom one is CO2. They basically showed that Corona has eliminated the last remaining benefit of CO2 lasers in this very important application. But With Corona now, when they need to do thin sheet, they switch to the small beam and get fiber laser-like performance for thin. So now they don't need two tools. You can do it with one tool and have all of the benefits in terms of reliability and power consumption, cost of ownership of a fiber laser. On top of that, Corona actually even gave them a larger process window. This is the focus position process window. With the standard fiber laser, it's plus or minus a millimeter. With the Corona donut beam, it's plus or minus 2 millimeters. So a larger process window, more reliable process. What we're seeing here is what we call no compromises performance. It's not like you have to choose, well, maybe it's a little better here. No, on all metrics, Corona is doing as good or better than a standard fiber laser and as good or better than a CO2 laser. So really no compromises, which leads these much more versatile universal tools such as the one HK has released. Let's now look at nitrogen cutting, and we'll look at here of stainless steel and aluminum. Here it's a little bit more subtle. With nitrogen cutting, particularly of moderate, few millimeters thick sheet, you always will go faster with a smaller beam, as I said, but the edge quality might not be optimum. And so with the versatility of the Corona beam, you can find the optimum trade space between speed and edge quality, and that depends not just on the material and thickness, but even on the application. Some applications demand better edge quality than others. And so here, two examples. This is from CY Laser, a tool integrator from Italy, and their Corona-based tool is known as Vega. This is right off their website, actually. This is 5 millimeter stainless steel with a standard fiber laser and with Vega, and you can see Corona gives this improvement in edge quality and to the point where they actually again said it's indistinguishable from CO2. Here's some results from a US tool integrator, Cincinnati, looking at nitrogen cutting of 19 millimeter aluminum, and here the goal is to reduce the dross along the edge. The dross requires some post-processing, so they want to minimize it. And so one standard thing to do is just buy more laser power, sort of throw more photons at the workpiece to try to minimize dross. But what they showed is that actually they could get less dross with 4 kilowatt Corona than 6 kilowatt standard fiber laser. What they're finding and others are finding is that not all photons are created equal. Basically, some are more productive than others, and you don't just want to sort of hurl more light at the workpiece. You actually want to optimize the delivery of those photons to give you the best result, and that's what Corona enables. So this is giving really unrivaled performance and versatility, and for instance, in this case, enabling lower power cutting. That gives you not just a lower upfront cost for the laser and the chiller, but lower operating costs, reduced power consumption, reduced contamination sensitivity of the optics. So it's sort of a benefit that pays off, with each part you make. Here's some actually very new results. This is from Hayag 26. They make cutting heads, so they're sort of one of our ecosystem partners. And they just came out with a new zoom cutting head called BMO FSC-L, and they're testing it with our newest Corona, our 12 kilowatt Corona fiber laser. And the idea here is they're saying, well, now we can change the beam shape, essentially with Corona, and for a given shape, zoom the size with their new cutting head, and let's see what result that gives. So here are just some of their results. They're actually going to be giving a talk at FabTech next week, so if you're there, they'll show many more results. I just have some of their early FabTech results. So this is 15 millimeter mild steel oxygen cutting, and here's with a standard magnification of 1.5. When you go from the flat top 100 micron beam to the donut beam, you get this sort of improvement in edge quality similar to what I showed you. And what they showed is that then if they go to 3x magnification, they get an even slightly a better edge quality and even more of an increase in the edge quality. Perhaps a more dramatic result came in piercing and cutting. They were looking at what's the optimum beam for piercing versus cutting and the optimum magnification. And they found for 25 millimeter aluminum, they basically used the same beam for piercing and cutting. There was no trade space there, so they used the 100 micron flat top with a magnification of 3 for both piercing and cutting. But when they went to 25 millimeter mild steel, the optimum had both a different beam size and shape for piercing and cutting, where they used, again, this small beam for piercing with magnification of 3.6, but the donut beam with 2.7x magnification for cutting. So what you're seeing is that a very large trade space being opened up that's really going to push the productivity of fiber laser tools to an even higher level, and all these benefits of fiber laser that I mentioned at the beginning in terms of lower cost and higher productivity, we're just going to see that keep expanding by bringing this beam size and shape into the mix. Let's now switch to welding, another important application, not as big as cutting, but actually growing faster than cutting these days. And what you find is that by changing the power distribution in Corona, you can change between this sort of keyhole and conduction weld. Remember at the beginning I showed you those two types of welds. When you use this smaller beam, you get a more keystone type weld, whereas it becomes more of a shallower, broader, a more conduction weld as you move power to the donut. These are all done at 3 kilowatts, all the same speed, but you see the different depths. What this turns out to be useful for is, depending on the material, you can significantly reduce the spatter, porosity, and cracking and improve the stability and cosmetics of the weld. You don't get all of those benefits simultaneously for all materials. You basically get to optimize among these things by tuning the Corona beam. So I'll show you one really important example, and that is welding of steel for a powertrain. This is with our partner Optoprim in Italy. And they were looking at powertrain welding, and in steel there's a real problem with spatter. Basically the keyhole will periodically close and then reopen and sort of eject out material. And that spatter sort of goes bad. Well, one, it can reduce the weld quality, it can lead to pores, but that spatter also goes places where you don't want it, either on the part being welded or on the optics. And so you really want to reduce the spatter. And so what they found, these are a couple of videos, is with sort of a standard 100 micron flat top beam, you can see all the spatter, whereas when they put some power out into the donut, you see much less spatter, and then you get a sort of smoother weld as shown here versus there. So this is really just some early initial results, but you can really see just with your eye how significant the improvement is. So let me now go back to this list of goals we were going for in a tunable beam quality fiber laser product, and the list is here. And a purely rational, dispassionate analysis leads you to conclude that actually Corona simultaneously achieves all of these. There's no other technology on the market that can say that. Certainly the other technologies achieve some of these benefits, but currently only Corona is actually able to obtain all of them. So hopefully I convinced you that Corona really does represent a breakthrough in fiber laser capability by providing this rapidly programmable or tunable beam quality. And being an all-fiber design, it overcomes the limitations of the previous approaches. We've already seen, as I showed you, very significant advantages for metal cutting, and not just us, but tool integrators and end users have experienced this as well. This has led to a number of new tools on the market from leading tool integrators worldwide. These are these sort of no compromises tools, much more universal, much more highly differentiated. Corona is also being recognized in the industry. This year we won the PRISM Award. This is an SPIE award they do every year at Photonics West for innovative new technologies, and we won in the industrial lasers category. In fact, tomorrow there's an award dinner here. There's a BlechNet Innovation Award, and we're a finalist, so we'll find out tomorrow whether we win, but we're already happy to be a finalist. I'm sure there are many qualified applicants. And with that, I'd like to thank you for your time. I'd like to invite you to our booth. We're in Hall 3, booth 3108, where you can see not just Corona, but our other industrial fiber laser products. And thank you again for your time, and I'd be happy to take any questions.